on which the Fields Institute operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, the Mississaugas of the Credit. Today, this meeting place is still home to the many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. And now I will introduce our speaker. I welcome everyone to today's seminar with Ankai Liu. Ankai is currently a third-year PhD candidate working on dynamical systems. He is working with Dr. Felicia Magpante on long transient dynamics. And today he will be presenting on their research on a quantification of long transient dynamics. So take it away.
Okay, thank you everyone to have me giving the talk. So let me share the screen. So basically this project is doing jointly with my supervisor, Felicia. So basically the approach might be quite different than what used to be here because I'm in a math major, so I trying to make things more abstract. So let's begin. So the presentation will be divided into basically 4 parts. So first one is introduction and motivation. I'll introduce what we mean by the long transient dynamic. And secondly, we will give some precise definition, and we will explore some of the behavior of the long transient dynamic. And thirdly, I will try to give a more quantification, give a way to quantify the long transient dynamic. And lastly, I will present some of the examples. So first of all, what we mean by long transient dynamic? Well, if some of you might be familiar with the disease model, and also some of you might have seen the SIR model, and there, in fact, you can often observe a phenomenon where the infected population stay very low for a long period of time, and of course after that it will rise up again and do whatever it wants. So here's a example right there. And the x-axis is the time, and the y-axis is the reported, in fact, basically the infected population. And if you look at this white yellow band right there, after the infected, after the vaccination, the infected population actually stay very low, around 0 for quite a long period of time. Notice the time scale here is by year. So it actually lasts for a year before the infected population rise up again. Then, so often the model will call this kind of behavior exclusively for disease model, the honeymoon period. And this, in fact, this is the kind of phenomenon that we are interested in. So roughly speaking, the long transient dynamic is a phenomenon where certain quantity V, so basically this acting like the measurement that you can observe or you are interested in, and this quantity appear to be stable for a long period of time. So in this case, well, the quantity V will be the projection onto the infected population, and of course you can see because the infected population stay quite low, around 0 for, right? So that's what it means by appear to be stable. And it lasts for 1 year. So if you consider a year to be a long time period, well, of course, this is gonna be a long transient dynamic. Just I want to point out that often this S and this TD, well, greatly depends on the model that we are working on. So it really depends on well, this S acting like the slowness, how slow you're considering to be slow, and this is capture the long, notion of long. So it really depends on what your definition of S and TD. Okay, so let me just give you one examples on what we are talking about there. So here is a simple dynamical systems. And we have the 3 plot right there. So the plot on the left is gonna be a XT plot, and the plot in the middle is YT, and the plot on the right is the phase plan diagram, which is the YX. So if we consider V to be the projection on x-axis, so that means we are looking at this plot right there, and you can see again, similarly to the SIR model, the x value stays around 0 for quite a long time, comparing to this bump right there. So again, just from eyeball, we kind of can observe the long transient dynamic in this model. And of course, I just trying to point out from the phase plan diagram, this long transient dynamic happening in this circle right there. So basically, this period of time happens around here. Of course, it's not very obvious just from the phase plan diagram, but this is what happening here. Another example is the SIR model, which some of you might be interested in. Again, the quantity often, the quantity we are interested in is the infected population. So we look at the IT plane. Also, I give you the phase plan diagram. If you look at the plot on the left, you can see here and here. Well, at the beginning of the dynamic, well, it seems to be the infected population seems to be small for a long period of time comparing to the rise and down, right? So also here and maybe here a bit, and of course, as time goes by, this phenomenon is not that obvious anymore. And if you look at the phase plan diagram, well, the trajectory goes like this, right? So it goes like from here to here. And the first long transient dynamic happens right here, basically. Happens in this region. So that's why you can see this clear long transient dynamic at the beginning of the time. But then as the trajectory goes by, as it goes here, it kind of stays away from this region. And that's why you don't see this long transient dynamic anymore. Okay, so but hopefully these 2 examples kind of give you some idea of what we are talking about right here. Okay, so before we go into to precise definition, I'll make the following 2 assumptions. The first one is basically assume that the dynamical system is solvable, has a global solution, basically. And the second one is assuming the global solution is continuous with respect to the initial condition. Okay. In fact, most of the dynamic that we have that we are studying will satisfy these 2 conditions. Okay, so let's get into the precise definition. So a given, let's say we are given a measurement V and given a dynamical distance, we can define dV as the directional derivative as this. So basically, this is the rate of change for V along the trajectories. Rate of change along the trajectory. Okay, so with this, we can define TS function as following. So this, in fact, this TS function is acting like the heating time. So if dV value at psi is less than S, less than or equal than S, then TS will be the increment of T, where T dV is greater than S. And if dV value stays less than S, then we say this heating time is going to be infinity, and of course, it's going to be 0 otherwise. Well, it might seem scary, but let's look at, so I hope this plot will be explaining quite well. So let's say we are given this S. So remember this S capture the notion of stability. So once we given, So once we given this S, we can split the whole space into a slow region and a fast region. Okay, so basically this TS, so you can see here, this TS is really the time it takes for the trajectory to enter this fast region. Okay, so that's why I'm call it. I sometimes think about it as the hitting time. So it's the time it hit the fast region, and of course we can look at this V along the trajectory, and you can see here, right, well before this TS, the V is acting kind of like stable before TS, but once it reached TS, the trajectory entered the fast region, and you can see the slope kind of becomes quite deep, and then we no longer consider it to be stable anymore. Okay, so of course, so let me just finish the definition. So let's say we have a TD. So this TD is acting like capture the notion of long. So we call psi a VSTD transient point if this hitting time is greater than TD. So that's why. So basically, well, it takes longer to enter the fast region. So that's why we can observe. So that kind of capture the long period of time kind of argument. And of course, we require it to be finite. Well, because if this is not finite, then the whole it's gonna be just a stable. And that's not quite interesting in our concern. Okay, so with the definition, we have let's look at the example right here. And this is the example we just showcased. Okay, I hope you remember this plot. And if we take V to be X, in fact, we can prove that for all S and all TD, there always exists a psi, which is some epsilon 0. So basically, some point right here, that is a VSTD transient point. So what it means is, well, no matter how slow you think you consider to be slow and how long you consider to be long, well, we can always pick a point right there. Pick a point right there that, well, the V value will change quite very slow compared to S, and it took as long as you want to leave this slow region. So in fact, in this example, we can see, well, this psi, this long transient point, are not actually that special, because for any set of S and TD, well, we can always find one. It's not quite unique in this dynamic. And in fact, this point right there, 0, 0, is truly the special point, because, well, it doesn't matter what S and TD we choose, as long as we stay close to this 0, 0, we can always find a transient point. So as like this 0, 0 is the source of transient dynamic, and therefore the 0 is truly the point that worth to study. Okay, so let's give it this kind of point definition. So, well, so for a given V, we call psi a V transient center if for all small enough S and all TD, and in every open neighborhood of psi, there is a VSTD transient point. Okay, and then we define psi to be a V transient center. So the reason we pick a point, pick the term center is, if you look at this example right there, well, for any S and any TD, you can always find a psi. That's as long as you stay close enough to 0, 0, it's always a transient point. So it is looking as like the 0, 0 is surrounded by transient point. And that's why we use the term center. And of course, in this statement, we can see that this statement exactly shows that 0, 0 is a V transient center. So we have this result right there. So hopefully that's enough to show you that, well, this definition successfully captured the notion of captured this 0, 0 right there. Okay, so with the V transient center, in fact, we can show some of the interesting properties. So one interesting property is this one right there. So suppose psi is a V transient center, then in fact, if we go forward in time and backward in time, the whole trajectory, every point on that will also be a V transient center. So in fact, that's very interesting. With this theorem, we can furthermore prove the second one, which is, well, if psi is a V transient center, then the dV value evaluated along the trajectory has to be 0 for all t. So this theorem is quite strong because, first of all, it gives us a necessary condition for psi to be a V transient center, and also it gives us a good candidate to find the points that are potentially to be a transient center. So this is the point that we are interested in. So basically, to find the long transient center, these are the good candidates. This capital psi is a good candidate. In fact, often in many dynamical systems, the psi is already strong enough. So once you put in this constraint, there won't be too much points left, and we can just evaluate each point one by one. Okay, so let's go back to the SIR model. In fact, we can show that suppose given all this constraint, well, these are just standard constraint on SIR model. And suppose your basic reproduction rate is greater than 1, we can prove that this point is actually a V transient center. And as a consequence of the theorem we just talked about, the whole set here are all V transient center. So so this result kind of agree with what we have learned before on SIR model. As long as your basic reproduction rate is greater than 1, we can always observe the honeymoon period. And in fact, this result backs it up. This one's not one interesting. So now let's shift our gear to another question, which is, given a psi and given a dynamical system, can you find a V such that psi is a V transient center? And in fact, the answer is yes, given some extra conditions. So I'm not gonna go in too deep right there, but I think this theorem basically tells us, well, given this condition right there, you can always find a V such that psi is a V transient center. Also, this theorem also introduced the example of non-existent OV. Okay, so let's look at another. So the next we want to look at is a sufficient condition. As we just introduced, big psi. So remember this big psi give a necessary condition for a point to be a V-transient center, but not a sufficient one. So is still interested in to look at what guarantees that a psi is a transient center. And in fact, what we found is this quantity right there, this quantity. And we noticed, we found that this quantity has a very close relation for psi to be a free transient center. And well, it's still an ongoing investigation, but hopefully I can convince you with 2 examples. So the first one, again, is the example we just looked at. And by direct computation, we can find that this capital lambda is actually equals to t times e to the power of half t squared. And in fact, as t goes to infinity, this term goes to infinity. And meanwhile, we have shown previously that 0 is actually a long transient center. So basically what I'm trying to say is this term goes to infinity has a close relation with psi to be a long transient center. And another example is, again, our favorite SIR model. And if we calculate this, again, we let V to be projection onto infected population, and we pick psi to be 1, 0, we can compute that this lambda is equal to this right there. So it might seem scary, but the most important term is this, right? And as long as this term greater than 1, and in fact, this related to the basic reproduction rate, okay? So as long as this term is greater than 0, and then this big lambda will go to infinity, and at the same time, psi is actually a V transient center. So again, you can see this tight connection between big lambda goes to infinity with psi being a transient center. So like I said, it's still an ongoing investigation. We're still trying to prove the connection between these 2 things. So basically, that's everything I want to present today. And thank you very much. And any questions?